Assalamualaikum and a very good day. And this is an example for a recycle stream where I will show you on the methods to solve for material balance calculation that involve distillation column. In this example here, what we have is a distillation column, and we are going to have a two recycle stream, which is from the partial condenser and also a partial reboiler. So let's look at the questions that we have in hand. Okay, the first thing is that we'll just go through the questions and then we will follow the structured method to solve the problems based on what we had pitched to you before. Okay. So we have a mixture of benzene and toluene, and this mixture is fed to a distillation column. So I will highlight that. We fed the mixture to a distillation column, the mixture of benzene and toluene, and the overhead stream from the column has 80 mole% benzene, and it is sent to the partial condenser where the liquid stream is recycled back to the top of column as the reflux. So we have the partial condenser, and this is where the recycled stream appear. And then we have the vapor stream, which is the liquid distillate. It is collected at 100 mole per hour. And the mole percentage or mole fraction of benzene is 85 mole%, and it is collected as the distillate product. And then the bottom stream, okay, that is exiting the column. Okay, this is the stream that exiting the column. It has 250 mole per hour of solution, and the content is about 25 mole% of benzene. So at the bottom of the column, we have another unit, which is a partial reboiler. A partial reboiler means some ratio of the stream is collected and some is heat up to produce a vapor phase and then sent back into the column. So a partial reboiler where the liquid stream exits and the vapor stream has a percentage of 20 mole% of benzene is recycled back to the column. Okay, and we call that one as a boil-up. The recycled stream from the condenser is a reflux, and the recycled stream from the reboiler is called boil-up. Okay, so the ratio of boil-up to the bottom product, which is collected as the liquid product at the bottom of the column, is 0.60, right? So we are required to find the composition and molar flow rates of the feed stream and the product stream from the reboiler. So when you are given this kind of problem, the first thing is that read the problem, understand what is given, what kind of information is given, and then look into what are the next step that you have to cover. All right. So as we had pitched before, first highlight the key information. So here we had highlighted the key information as we go along. Okay. Next is to draw the block diagram of the system. Okay, I had prepared a block diagram here. Okay, so this is a distillation column, and we have the feed stream, we have the vapor stream, we have the distillate where the product is collected. The reflux is where the recycled stream is going back to the column. Okay, and then down bottom of the column, we have the liquid phase that is then sent into a reboiler. Part of it sent into a reboiler as a boil-up, which goes back into the column, and some are collected as the bottom product. So let us label the stream first before we move and label all the values respective to the given values. Okay, so we are going to label the stream from left to right. Stream number 1. This is stream number 2. This is stream number 3. Right? We have stream number 4 going as a reflux. And then stream number 5 that is going as a liquid phase that's exiting the bottom of the column. And then we have stream number 6, which is the bottom product, and stream number 7, which is the boil up. Okay, so what are the known information that we have? Okay, let us do and label everything here. So we know that the basis that we have here, okay, I'll write the basis is 100 mole per hour of distillate. All right, that is our that is the basis that we have. So it is 100 mole per hour of distillate. So what we have now is, this is stream number 1. It is in mole basis, so I will put the label as N1. There are 2 components that we are working with, but to simplify the values, then we are going to use just 1 terms. All right, so for a mole fraction of benzene in stream 1, we are going to label it as X1B. And the other component that we have, which is toluene, we will label it as just 1 minus X1B. So that will only leave us with 2 unknowns for stream number 1. Okay, the same goes with stream number 2. So we are going to label it as N2, X2B, and 1 minus X2B. Right? That's what we have. And then we have stream number 3, which is N3, X3B, and 1 minus X3B. Stream number 4, we have N4, X4B, and 1 minus X4B. Okay, going down the column, we have N5, X5B, and 1 minus X5B. Okay, last one is there are 2 more, and 6, X6B, and 1 minus X6B. All right, last one, N7, X7B, 1 minus X7B. Okay, let's look now what are the known and which one are the unknowns, right? I'll just put it a different color so that we are able to see. Okay, based on this information here, we have the overhead stream from the column, which means it is stream number 2, right? So it has 80 mole percent benzene and sent to a partial condenser. So that one then says this X2B is 0.80. Okay, what is the unit? The unit is mole per mole of B. So this will leave this one to be 0.20 mole per mole of T. Okay, what are the informations that we have? That one is taken care of. And then we have the liquid stream is recycled back to the top column as a reflux. Okay, no other information. The vapor stream, which is 100 mole per hour and 85 mole percent benzene, exceeds the condenser. So let's go and check where is the condenser. This is our partial condenser here. Okay, that is our partial condenser. This is our partial reboiler. Okay, so we're going to label that as N3, which is 100 mole per hour. And then our X3B is 0.85 mole per mole of B, right? Then that leaves the toluene to be 0.15 mole per mole of toluene. Okay, so we are not given any information on N4, X4, and or toluene values. Okay, let's move down the column. Okay, so what are the information that we have down the column? Let's look back. Okay, we are going to look back here. Okay, so we had completed that. Now we are going to look down at the bottom stream. Okay, it has 250 and 25 mole benzene. And then we have a liquid stream exiting as product, which is 20 mole percent of benzene is recycled to the top column. Okay, so those are the information that we have to put into here. Okay, so we are going down. So it is said that this is 250 mole per hour. Okay, how much benzene do we have there? We have about 25 mole percent of benzene, right? So we have 25 mole percent of benzene. So it says that it's 25 mole per mole of benzene, and we have 0.65 mole per mole of toluene. Okay, and the next one that we have is the fraction of benzene that is recycled is 0.20 mole per mole of benzene. So this one here has 0.80 mole per mole of toluene. Okay, but we don't know what is N6. We don't know how much that is produced as a bottom product or collected as a bottom product. We don't know what is the benzene fraction. So this actually gives us some ideas on what are the knowns and what are the unknowns. All right, so let us recheck again on what are the information that we have, just to want to make sure that we have everything. Okay, so other information that we have is that, okay, this is the other information that we have. I'll show it to you here. The ratio of boil up, okay, ratio of boil up, which is our N7, right, divide by N6 is equals to 0.6. Or we can say that N7 is 60% of N6. All right? It is 0.6 of N6. Okay. That is the other information that we have. Okay. Now, let us set our boundary. How do we set our boundary? Remember, we have to set the boundary when we know there are changes in terms of the property of the stream. So the first boundary that we are going to set is, okay, let's do and change the color now. The first one will be the overall. The overall will cover this stream here. Okay, that is A. And then we have the second one, Make it a little bit thicker. Okay, the second one will be around our column. Okay, because around the column there are changes. So this is B. Just change it a little bit. Okay, that is B. And then we have another one. Okay, which is around our partial condenser. And the last one is around the partial reboiler. Okay, those are the 4 boundaries that we can look and investigate. So let us look at it one by one, yeah? We're going to look at it one by one and do the boundary analysis. We're going to do the degree of freedom analysis. Let's say boundary A. Okay, our boundary A. What is in the boundary A? How many unknowns? Okay. So boundary A, the number of unknowns. How many unknowns that we have? So boundary A are, we can say it's stream 1, we have stream 3 and stream number 6. All right, these are the stream that we have. So how many unknowns that we have? We have, let's say, let us label the unknowns. We have N1, we have X1B, we know N3, we know X3B, we don't know N6, and we also don't know X6B. All right, so our unknowns are 4. All right, what about the number of species or number of compound? So we have benzene and toluene. So there are 2. Okay, we have benzene and toluene. So those are 2. Is there any other information? That is 0. So it's 4 minus 2 minus 0. The DOF for boundary A is equals to 2. Okay, let's look to the next one. The next one that we have as our boundary is boundary B. Okay, we have boundary B. What are the unknowns? All right, number of unknowns. What is our boundary B? It is around the column. All right, this is a column. This is the overall. So what do we have in our column? So within the column, we have the unknown as N1, X1, N2, X2 is known, N4, X4, N5 is known, X5 is known, N7 unknown, X7 is known. So unknown is N1, X1, N2, N4. Okay, so our unknowns are N1, X1B, N2, N4, X4B, and then we have N7. So how many do we have? 1, 2, 3, 4, 5, 6. There are 6 unknown. Okay, how many species that we have? We have two species or two compound. Any other information? Okay, other information? No, there is no information. So 0. So we have the DOF for boundary B is 4. Okay, let's look now to boundary C. Our boundary C is around the partial condenser. Okay, so how many unknown that we have around the partial condenser? Let us list it down. We have N2 and we have N4. We have X4B, right? So there are 3 unknowns. How many species that is there? Or how many compound that we are working with? There are 2. Any other information? No, it's 0. So we have 3 minus 2 minus 0, that is 1. Okay, the last one is our boundary D. Which is our partial reboiler. Okay, how many unknowns that we have in the partial reboiler? We have N6, X6, B, and 7, right? That is what we have as the unknown. So that will be 3. How many species that we have? That will be 2, all right? Which is benzene and toluene. And then what else? We are working with other information. Do we have any other information? Yes, we have 1. Okay, so we have 1, which is N7 is equals to 0.6 and 6. That is the other information that we need. So this will make our DOF around the partial reboiler has equals to 0. So where should we? So first, we have to solve at the partial reboiler first. All right, so let us set up our material balance equation since our partial reboiler, okay, our partial reboiler has a DOF equals to 0. So we're going to solve for or set up the material balance equation at partial reboiler and then solve the equations directly. So what are the stream that is going into partial reboiler? Let us do a total stream or total material balance first. So our total material balance will be N5 is equals to N6 plus N7, right? So why can we add in mole here? Because there is no reaction, there is no accumulations, right? It is a continuous steady state process. So the mass in or the moles in is equals to the mole out. So we have N5, which is 250 mole per hour is equals to N6 plus N7. We also have the information just now, remember? Okay, so I will put this one here as 1. So we have the information where our N7 or the stream that goes into the boil up is equals to 0.6 of N6. And 6 is the stream that is collected as the bottom product. So we have that as equation number 2. So when we replace number 2 into equation number 1, so we're going to plug in 2 into 1, then we have 250 is equals to and 6 plus 0.6 and 6. So we have 250 is equals to 1.6 and 6. Therefore, N6 is equals to 156.25. The unit is mole per hour. Okay, so 250 divided by 1.6, so we have 1.6.254 and 6. Okay, let's do the molecular balance for the compound. Here we have the information for benzene. So we're going to write for benzene, we have the inlet stream, which is N5. Okay, X5B is equals to N6 X times X6B plus N7 X7B, right? So we have N6 X6B and N7 times X7B. So we can replace the values that we have. You have to make sure that the units are consistent for the inlet and outlet. So we have 250 mole per hour of the inlet feed to the partial reboiler. And we have X5B, which is 0.25 mole per mole of B that's coming in. And then we have our N6 from the previous calculation, which is 156.25 mole per hour of the outlet or the bottom product times our unknown fraction of benzene that is in the bottom stream plus N7, which we can calculate from this relation here. So we have 93.75 mole per hour of the boil up stream, okay, times the benzene fraction in the boil up stream, which is 0.20 mole per mole of benzene. So you can check that the units are consistent, then we can do the mathematical equations for this material balance. Okay, so we have 250 times 0.25, that is 62.5. Okay, and we have 156.225 X6B plus 93.75 times 0.2, we have 18.75. Okay, so we have total of so when you do the mathematics, then you are able to get X6B will be equals to 0.28 mole per mole of benzene. Okay, so the toluene amount will be X6 toluene will be 1 minus 0.28, and that will be 0.72 mole per mole of toluene. All right, so we have the information for the given partial reboiler. All right. Okay, since we already solved some of the unknown stream, let us recheck our boundary. Which of the unknowns that can be cancelled now so that we are able to reduce the degree of freedom for some of them for us to be able to solve them. All right, let us look one by one at our boundary, the boundary that we have. So for the overall system, we already have 6, we know N6, so now our unknown is reduced to 2, so we should be able to solve it. All right, so this is solvable now. Let's look at boundary for column B, okay, boundary B. So we don't know N1, we don't know X1, no information on N2 yet. N4 is not known, but we already solved for N7, so we are down to 5. Okay, so we're down to 5. Now this is going to 3. Okay, boundary C, a partial condenser, no solution yet, so it is still 1. Okay, let's now go into our overall material balance. So the overall material balance will be around boundary A, right? It is in boundary A. So what do we have in boundary A? So our total balance, okay, our total balance stream will be N1 going in will be equals to N3 plus N6, right? So N1 is equals to N3 plus N6. That will be N1 okay, N1 is equals to N3 is known, which is 100 mole per hour. We know N6 just now, which is 156.25 okay, mole per hour. So we are able to solve for N1. So N1 should be equal to 256.25 mole per hour. So that is our N1. Let us solve for our molecular or compound balance. So again, we have information for benzene. So we are going to do the molecular balance. So the molecular balance will be on benzene. So what are the material balance equation that we can set up for the overall system? We have N1 times X1 benzene is equals to N3 times X3 benzene plus N6 X3 benzene. Sorry, X6, okay? And 6 times X6 benzene. So what are the information that we know? We already know N1. So N1 is 256.25. We don't know the mole fraction of X1, so we'll just leave it as an unknown. we know N3 is equals to 100 mole, and then the XB3 is equals to 0.85, and then we have N6, which is 156.25, and our X6 benzene, let's look at the results that we have. X6 was 0.28, right? 0.2. Okay, have to make sure units are there. So our X1 benzene is equals to, okay, we have 85 plus, we have 43.75 divided by 256.25, and we are getting 0.50 mole of benzene per mole. So the respective mole fraction for toluene in the inlet stream will be also 0.50 mole per mole of toluene. So we solve all the required problem with respect to the unknowns, right? So we solve for N1, we solve for X1, B, and T. We solve for N6 and X6, B, and T. Okay, let us now look back into our DOF. Any changes on the DOF that we have, okay, going from the boundary B. Okay, boundary B, now we know this is known, this is known. N2 is not yet, N4 is not yet, X4 is also not identified yet, so we still have 3, and we have 2 species, so this one here is going down to 1. For boundary C, we still have N2 unknown, N4 is unknown, and X4 is unknown, so it remains as 1 DOF. So we need other information to be able to solve for the rest of the unknown.